Okay, so last time that we talked, we were into chapter 6, and we started talking about nomenclature, which again is a fancy way of naming things. And really, we talked about kind of two types of compounds, bonding compounds. We have, again, ionic compounds, which are metals and nonmetals. And remember that we do get, as we'll talk about here, a transfer of electrons in this case. And that again is going to result in really ions being formed. And we're going to have cations formed, which are positively charged, and anions that are negatively charged. And when we go to sort of name things, pretty much it is always the metal, as we talked about. That's really important. So whenever you go to name anything, you have a compound and there's a metal involved. That is always the one that you want to look at. It really will determine how you go about naming it. So we talked about the idea of type 1 compounds, which are ionic compounds. And type 1 compounds, again, it's that metal that's most important. It is going to have a fixed positive charge. And the way you could recognize that, again, is its location on the periodic table, pretty much. If it is from group 1, 2, or 3. And remember, from group 3, it's pretty much aluminum that we're talking about in most cases from group 3. Or from the transition metal, remember, there are 3 transition metals that have basically fixed positive charges, and that is zinc, cadmium, and silver. Those guys also will only form one type of charge. So remember that as soon as you sort of identify the metal in this case as being a type 1 metal, all you have to do is essentially go whole name of the metal. And the non-metal, again, gets the IDE treatment at the end. Again, we do drop a little bit of the non-metals part of the name at the end, and we put IDE in its place. Also remember that we never ever, as we talked about, use prefixes when we have a metal involved. So that's usually a for sure wrong answer if you're using any type of prefix in this situation, if there is a metal involved. Now, along with that is type 2 compounds, and type 2 compounds are also, again, ionic. And once again, it is the metal, as we talked about, that's most important. And the metal will, in this case, come from a transition metal, or as we talked about, just to the right of it, under the staircase. And what basically these metals have in common, as we talked about, is they have the ability to make a variable positive charge. So in certain cases, they may be like +1. In other cases, they may make a +2 charge, or maybe a +3 charge, and so forth. So unlike type 1 sort of metals, which no matter who they hook up with, no matter how many of whoever they hook up with, they're always just going to make that charge. So something like sodium, which is a type 1 metal, you could put sodium with whoever you want. It's only going to make a +1 charge. It'll never make like a +2 charge or anything like that. So it's like fixed in stone. Now, the transition metals are different. In that case, it does kind of matter who they're hooked up with, and they have that ability to actually make a variable type charge. And that means that once you identify as the type 2 that has a variable charge, you have to sort of figure out what is the charge on the metal. The good news is that you will always know the charge on whatever is hooked up to. So whatever that transition metal is attached to in that ionic compound, you should be able to basically figure out the charge of that. And you can kind of work your way backwards to figure out the charge on the metal. Remember that when we put a metal and a non-metal together, a cation and anion together, the overall charge doesn't equal 0. So in the simplest way possible, and that's basically how you want to try to balance it out. So, you know, you will use still the whole name of the metal. we will need to include in this case a Roman numeral. And again, remember, as I mentioned before, the Roman numeral is the positive charge on one of the metals. So not the total charge that you get if there's multiple of the same metals. It's not how many metals you have, which is a very common error that people make. It is if you took one of those positively charged guys out, what the positive charge would be on it. And that's what the Roman numeral is. The nonmetal is still the same. It's still going to be our nonmetal that has that IDE treatment at the end. Once again, does not matter how many of each of those that you have. Because a metal's involved, we still will not use a prefix in this case. So it does not matter if you have a lot of the metal. It doesn't matter if you have a lot of the non-metal. Once again, the way you should remember it, like we talked about last time, if you see a metal, you should not be using prefixes, no matter what the situation is. No matter if your heart tells you you want to do it, don't do it. It's going to be wrong. Now, these are ionic compounds. Again, there is no sharing of electrons in this type of bond. It is just the positive and negative attraction between the two ions. When we do these guys, it is always cation first, followed by anion, both in the formula and when you name it. So when you name it or write the formula for it, that is always the order that it should go in. We then talked about type 3 compounds, and type 3 compounds are actually covalently bonded together. And that basically means that we have sharing of electrons happening. And because of that, there really is no ions or anything like that. There's no charges to worry about it. It's going to basically be two nonmetals together. So if you see two nonmetals together, that's going to be a type 3 compound. And as we talked about, this is the place where you should use prefixes. So again, we have mono, which is 1. We have di, which is 2. Tri, which is 3. Tetra, which is 4. Penta, which is 5. Hexa, which is 6. Hepta, which is 7. Octa, which is 8. Nona, which is 9. And a little deca action, maybe that is 10. Now, when we use these prefixes, there are a couple rules and there are a couple of things that do occur that we need to be aware of. So one of the major sort of rules is we do not use, again, mono on the first name. But it is, again, okay on the second name. Now, in addition to that, what oftentimes happens as well is when you go to use a prefix and you go to use the element name, the first letter of the element name, you will sometimes get two vowels that back up to each other. So the most common sort of cases of that, again, is you will have like two O's that come back to back, one O from the prefix at the end and one O from the element at the beginning of the name, like oxygen. In that case, we typically get rid of the prefix vowel. Also, an A and an O is a common sort of thing that will happen, and we get rid of the A from the prefix as well. So I think we looked at monoxide, which is not what we call it. We call it monoxide. So again, we get rid of one of those O's. How you go about naming this is you use the prefix for the first element, if needed. Obviously, the only time it would not be needed is if it's mono. And use the whole name of the first element. Again, for the second name, you're going to use your appropriate prefix. And the second name does sort of roll like normal nonmetal. It will do the IDE at the end of it. So again, like carbon monoxide, it was an example we looked at, carbon monoxide. Again, here, that is a capital C, capital O, which is carbon and oxygen, two nonmetals. We do not use mono, which is how many we have there, the first guy, but we can, again, use it on the second name. and that's okay. And again, that would be a case where we would have, if you just wrote it monooxide, the two O's would back up. We would want to get rid of the first O from the prefix. And lastly, we got into or started talking about polyatomic ions. And polyatomic ions are interesting things. They are actually, again, compounds or ions that actually do share electrons because they are groups of nonmetals together, which means they will share electrons. But based on who they're sharing it with and how the electrons are shared, they actually will end up with an overall charge, which actually makes them ions. So I think at the end there, we looked at NH4NO3, for example. And again, if you broke this up right about there, we have two ions, polyatomic ions, that is NH4 with a +1 charge. And once again, that nitrogen and 4 hydrogens will not break apart. They will always move around as a whole unit. And that again is because they are actually sharing electrons. So they're sharing electrons there. So they're just going to move around as a whole unit. That entire unit basically has a +1 charge. So even though there's one nitrogen, 4 hydrogens there, overall, the whole entire thing has a +1 charge. Same thing with this guy, which is nitrate. That one nitrogen and 3 oxygens also are going to be sharing electrons and moving around as a whole unit. And that whole unit will have a -1 charge. And that is why when we put it together in our formula, we pretty much just need one of each of them, because that's again back to 2 ions. So whenever we put anything that is a positive ion and a negative ion, in this case, even though they're polyatomic ions, we still want to balance the charge to 0. So again, +1 and -1 means when we slap this together, we basically just need one of each of those guys, and we'll balance out the charge. Now, polyatomic ions do have special names. And again, that is what is known as the ammonium ion. And this is what is known as the nitrate ion. And with polyatomic ions, it does not matter how many of those ions you have. You just simply use the whole name of the polyatomic ion. So just rolls with the whole name. In this case, since they're both together, this is what is known as ammonium nitrate. And that would be the name. And again, it wouldn't matter if I had like 3 nitrates in that case or 4 ammoniums. It would still just be called ammonium nitrate in that particular case. Now, again, here you do need to balance out charges. With our type 3, remember, again, there is no charges you need to worry about, just the appropriate prefix. And obviously here with our ionic guys, type 1 and type 2, you do need to balance out the charge. Now, as we also mentioned at the very end, and we'll talk a little bit more here again, I would say that that guy right there is going to be probably your most common positive polyatomic ion. The vast majority of polyatomic ions are actually negatively charged. So most of them are negatively charged. And that means that I would say probably 99% of the time, maybe even more, you most likely will find a polyatomic ion hooked up with a metal. So it's going to probably use a metal for the positive ion in this case. And that means that when that happens, what you're probably going to see is something like this. Again, a metal with a polyatomic ion. And what that means, again, as we talked about earlier, as soon as a metal's involved, that is really where you should focus your attention to. And at that point, what you should try to decide is that metal a type 1 metal or is it a type 2 metal? And again, basically what you're trying to decide in that case is, do you need a Roman numeral or not, basically. So if it is a type 2, you will again have to figure out the charge on the metal and use the appropriate Roman numeral in that case. Any questions on that stuff there that we talked about last time there? Now, a couple of things before we get too far into that, I think. Now, let's just talk a little bit before we continue on with polyatomic ions. Let's just talk about a couple of things that's important. Again, a reminder that there are certain things that have sort of common names that we use. And again, H2O, as we might have saw last time, again is water. So you should always use water for H2O. Once again, is not a trick question. It should be like a free point. Yeah. So that is, don't write all kinds of weird things for water. Just write H2O is water. NH3, which was we just saw, is different than NH4 plus, and this is ammonia. Again, not to be confused with the polyatomic ion that is ammonium. So again, the polyatomic ion has one more hydrogen and actually a charge. This guy, one less hydrogen, no charge. And CH4, which is methane. And that again is a simple organic molecule. We definitely will see it again as we get into the organic chapters. Now, hydrogen is a little bit different in the way that we sort of name hydrogen when it's involved, and how we kind of go about naming things that have hydrogen in it. So hydrogen, even though it is technically a nonmetal and technically it will covalently bond with things, it does behave a lot of times in solution kind of like a metal, and it behaves a lot like a type 1 metal. And what that means is, even though again hydrogen is not a metal, it is actually a non-metal. When we have hydrogen and we're naming something with hydrogen, we oftentimes think of it as being H plus, like the hydrogen ion. And we basically would name it as such. So if you had HCl, and for example, if this was a gas, this would be called the hydrogen, it would be called hydrogen chloride here, gas. If you had HBr, that would be hydrogen bromide. If you had H2S, this would be known as hydrogen sulfide. So you can see that even though, for example, we may have in that last one 2 hydrogens involved, and even though technically it's a nonmetal, we do not use a prefix with it. We name it more like a type 1 type of metal, even though again hydrogen is a nonmetal. The reason we do have 2 here is because sulfur is group number 6 on the periodic table, which means it has a negative 2 charge, and each of the hydrogens is +1, and that is why we need 2 of them there. +1 and +1 is +2. That balances out the -2 charge that is present in that particular case. Yeah. What the G means gas. That's in the gas phase. Yeah. And I put that because although we won't talk about it at this point, if you actually have HCl in what is referred to as the aqueous phase, which is AQ, it's actually an acid at that point, and it actually would be named differently. It would be hydrochloric acid. So this is how you get to hydrochloric acid. You take the hydrogen chloride gas and throw it in some water, and basically it'll make some hydrochloric acid in that case. So that's why sometimes you'll see the distinction, especially with things with hydrogen, like the states and stuff like that, because if you technically see the AQ in anything like that, or even an AQ for like this guy as well, that would actually be an acid as well. But sometimes people will still just go by hydrogen bromide or hydrogen chloride, even when they're kind of talking about an acid and stuff like that, but there's a difference. We will talk about acids and bases in a later chapter, and we'll just go over quickly how to kind of name acids and stuff like that, just so you have an idea of how to do it and when you see it and what it's called and stuff like that. Yeah. But for now, if you see something like HCl, you could just call it hydrogen chloride. It's fine. Yeah. But if you wonder why sometimes maybe you see it as called like hydrochloric acid, that's the reason, basically. Yeah. Other questions? Okay. So that's hydrogen. Good. All right. So let's get back to our polyatomic ions. So there's a table, I think on Canvas as well, that lists them all, and also in your book. And these are similar tables to what's in there. But let's talk about how you can sort of understand and figure out the names of these guys. And there are patterns to the polyatomic ions, which will help you sort of identify them and know which one you're talking about. So usually when we look at polyatomic ions, there are ones that are related to each other in groups of 2 usually, or sometimes in groups of 4. And there is a sort of pattern to what you see. So for example, if we look at this one here, which is NO3 minus that we saw earlier, and again, that entire thing has a -1 charge. And we look at NO2 minus, and again, that entire thing has a -1 charge as well. This is, as we saw earlier, the nitrate ion. This guy is actually known as the nitrite ion. Now, if we look at something like SO4 2 minus, once again, the 1 sulfur and 4 oxygens are going to stay together as like a group. The entire thing has a -2 charge. This is what is known as sulfate, ATE. And if you have SO3 2 minus, this is what is known as sulfite. Now, when you're looking at sort of a group of 2 that are related to each other, let's just analyze sort of what is the difference between these guys. So let's take a look at the nitrate and nitrite. The overall charge in each of them is -1. So is that the same or different? It's the same, right? They both have a nitrogen. That's the same. So what is the only difference between those two? The number of oxygens. Yeah, this one has 3 oxygens. This one has 2 oxygens. Everything else is identical to each other. Yeah. Now, when we look at sulfate versus sulfite, they both have same charge, right? They both have a -2 charge. They both have the same sulfur. And in the case of sulfate and sulfite, what is the only difference between those two? The number of oxygens, right? So in a grouping of 2, the one that actually has the most oxygens will usually end in 8. Yeah. How can you remember that? I ate too much. Yeah, most oxygen. Yeah, that's a good way. Yeah. The one that has the least number of oxygens in a grouping of 2 will end in 8. So that's a really good way to kind of group these guys together that are related to each other. And what you could do, for example, is if you want to remember like all the ites, all you have to know is the 8s are just 1 more oxygen. Everything else is the same. Or you can remember the 8s and remember the ites are just 1 less oxygen. So you don't have to necessarily remember them all or anything like that. And to really quickly remember them, you can just remember all the 8s or all the ites and just know how to adjust it, either add an oxygen or remove an oxygen. Everything else, again, will be the same. Now, there are a couple of other things that we see on this table in terms of relationships. You can have actually a grouping of 4 that are together, that are related to each other. And probably the most common one is this grouping of 4 right about here with chlorine in it. And that is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Once again, every single one of these guys all have what type of overall charge? They all have a -1 charge. Yeah. So every single one of them has a -1 charge. Now, in a grouping of 4, you could actually do the same thing. If I split it right there in the big opening there, everybody to my right has the least number of oxygens, right? And everybody to my left has the most number of oxygens. So I already know that my guys on the right there should end in 8 or 8. They have the least number of oxygens, so they should end in 8. So this would be chlorite. This would also be chlorite, right? They basically both should end in "ite." Clearly, you cannot have 2 names for 2 different things or the same name for 2 different things. So in a grouping of 4, the one that has the least number of oxygens out of all of them will end in "ite," but will also start with hypo. Hypo means less than, basically. So it has the less number of oxygens. So that is hypochlorite. That is chlorite. Now, when we go to the ones on the left of my line on top, those are the ones that have the most oxygens, which means they each should end in 8, right? So most oxygens end in 8. This will be, I'll come down here, chlorate. This guy will also be chlorate because it has the most number of oxygens. But just like on the right-hand side there, we can't have the same name for two different things. So in a grouping of 4, the one with the most oxygen will also start with per. So perchlorate, chlorate, chlorite, and hypochlorite. They all are related to each other by the number of oxygens. Again, they all have a -1 charge. They all have 1 chlorine. And the only difference is the number of oxygens that are present. You could do the same thing as I just mentioned, which is, let's just say you remember this name, right? Chlorite. And you need hypochlorite. That's the one with the least, which means all you have to do is subtract off 1 oxygen. Everything else stays the same. Or you need chlorate. Add 1 oxygen, right? Everything else stays the same. You need perchlorate, add 2 oxygens. Everything else stays the same. Yeah. Yeah, so you need to know, for these, you need to actually know the formulas and the charges that go with them so you're able to balance out the formulas correctly. So they are fixed in the sense, for example, if that's your question, like if like chlorite will never be anything other than -1, if that's your question. Yeah, so yeah, it will never change. So just like nitrate, it will always be -1, just like sulfate will always be -2. And so the names that go with these polyatomic ions and the charges that you see are fixed in that sense that that name represents whatever the charge is in the formula. Yeah. Other questions? Now, a couple other things that you will see on this chart, or a chart like this, is, for example, if we take CO3 2 minus, that is, as you can see here, carbonate. And sometimes we may put a H plus onto that, and that's an HCO3. And by the way, when I have +1 and -2 and I add that together, what am I left with? -1, yeah? So 2 minuses and only 1 plus leaves you still a minus left over. What I basically just did on that is put a what element? Just put a hydrogen on it. So we put that in front of carbonate. That is now known as hydrogen carbonate. Basically just put that hydrogen in front of it. Now, there is a historical name for this guy that people still commonly use, and that is what is referred to as bicarbonate, right? Got a little heartburn action right about now, yes. So bicarbonate is also sometimes used instead of hydrogen. You will also see that with sulfate, hydrogen sulfite, bisulfite, hydrogen sulfate, bisulfate. Those are just sort of older names that people still use, like when you buy sodium bicarb, right? Baking soda. Yeah, basically. That is basically what it is. Yeah. So again, like I said before, you do need to kind of know the charges to go with these and the names so that you can put things together correctly. And again, these most likely will be hooked up with a metal in most cases. So let's take a look at one. Well, this is another chart as well. So why don't we do a few here? What would be the name of? Let's do that guy. Let's do that one. Let's do that one. And why don't you write the formula? Whoops, come back. Why don't you write the formula for, let's see here. Let's go. Nickel to sulfate. Calcium hydrogen carbonate. And what's write the formula for, let's do, ammonium sulfide. All right, so give it a go there. Let's do proper names on the left there and formulas on the right. See what you come up with. Okay, so let's take a look and see how you're doing. So once again, whenever you're naming anything, as we talked about, probably the first thing you really want to do is sort of identify what you're dealing with, right? Because if you know, hey, I got a metal and a non-metal, or I got two non-metals, that should hopefully direct you in the right place in terms of naming it. So clearly here I have a metal and I have a polyatomic ion here. So once again, whenever the metal's involved, that does tell us that is the most important thing to look at. So we do want to look at the metal, which is iron. And once again, iron is dead center of the transition metal region, which should automatically tell you that is a type 2 metal. And that means Roman numerals should pop into your head as to I need to incorporate some Roman numerals. So I also need to figure out the charge on it. So I do know from the formula here that I got just one of those irons hanging out. From here, when we got our polyatomic ion, that is carbonate, which is CO3 2 minus. Once again, the entire thing here for carbonate is -2. That means to balance it out to 0, the one iron would have to have what type of charge? +2, right? To balance out, +2 -2 equals 0. That again is all you need now to name this. You're going to go iron, just like we did with our metals. Roman numeral 2, once again, that is for the charge, not how many you have. And once we get to the polyatomic ion, we just roll with the whole name of it, which would be carbonate in this case. Question on that? Yeah. It would be, I would imagine, yeah. Provided it says iron in front of it and not like some other element. But yeah, it's yeah. Other questions? All right. Taking a look at the next one. Again, we see a metal. We see another polyatomic ion. Once again, that is where we want to look, which is our metal always. We go to the periodic table and we can find that metal in group number 1. Because it's part of group number 1, it should now tell you it is a type 1 metal, right? Which means it has a fixed positive charge. And that is a type 1 metal. The good news about type 1 metals is I don't really care about charges and balancing because it doesn't matter. At this point, I could just go to naming, right? I'm just going to use the whole name here of it, which is sodium. Again, because it has a fixed charge, I don't need to worry about the Roman numeral, right? I'm not going to use that. And then once again, we're going to roll with our polyatomic ion, which, by the way, this is Na plus, and that is NO2 minus. And that NO2 minus, again, is different than NO3. That, to me, seems like it has one less than NO3, which is nitrate. So because it has one less than nitrate, that then means it's nitrite, I-T-E, right? So again, these are the things you want to kind of think about as you're doing it. This is also why the formula, we just need one of each of them, +1 and -1, right, gets us to 0. And that's why we just have basically one of each of them there. Yeah. You don't, if it helps you do it, but you don't need to. So again, if you had a question like this, ultimately that is what I'm looking for, right? The name at the end. But if it helps you to do that, you can. The only time you would need to do that if you had a question, for example, that said, write the formula for the cation or write the formula for the anion in this case. And if you did have a question like that, this Na plus would obviously be the formula for the cation, and the NO2 minus would be the formula for the anion. But if you were just asked simply to name this compound, what I circle there is basically what you need to get to. Yeah. Other questions? And again, I show all the charges and all that type of stuff just to hopefully help you see where we're getting the name from. It just doesn't pop out of, the sky or anything like that. Here we do have Cu, which is copper, which is a metal. OH is OH minus. It is one of the few, and there are some polyatomic ions that actually have IDE at the end of their name. So there are a few: cyanide, hydroxide, azide. There are a few polyatomic ions that actually have IDE. Normally we associate IDE with somebody just from the periodic table, right? Those nonmetals from the periodic table. But there are a few sort of polyatomic ions that have that sort of ending as well. Most of the polyatomic ions are going to be 8 or I8s, but there are a few like that. So once again, we're going to look at our metal. And again, our metal here is in the transition metal region, which tells us, once again, like the first one, that is a type 2. And that is also some Roman numeral time. We need to figure out the charge. So in this case, we have 1 copper. Not sure what the charge is. I do know here that my hydroxide is -1. And how many hydroxides do I have, by the way? I do have 2 of them. So that means 1 and 2 is a -2. That would mean that the copper would have what type of charge? +2 to balance it out. And again, as soon as I realize what the charge is, I am ready to name it. We're going to again use the whole name of the metal, which is copper. Here we will use Roman numeral 2. Once again, from the charge here, and the whole entire name of the polyatomic ion. Once again, it does not matter that you have 2. This is still hydroxide. Once again, that is a metal, no prefix, right? So that is why the only place you will ever see probably a metal with a prefix is if you happen to have a polyatomic ion that actually has it as part of the name, like this guy. This guy has a prefix as part of the name of the polyatomic ion. That is the only place where you will ever see a prefix with a metal involved. And it just happens that the polyatomic ion has that prefix in it. But other than that, you should never use it. By the way, why did I again use parentheses on that OH there? And again, why did I not just write it like this? When I write it like on the bottom, how many hydrogens do I have? And how many oxygens? 1. But that's not really what I want, right? I really have 2 of those and 2 of those. I have 2 of the OH units. So whenever you have more than 1 polyatomic ion and you need to put it into a formula, you should always put parentheses around the polyatomic ion. And on the bottom right should go how many of those units you have. Otherwise, you may be saying something that doesn't really exist because, again, you'll be short some stuff. Question on any of those names there. All right, then let's go from name back to formula on the right-hand side. So nickel, Roman numeral 2 sulfate. So when I see nickel with a Roman numeral 2, what does the Roman numeral tell me? The charge on the metal. So I don't even have to figure out anything. It just told me right up that that nickel is carrying a +2 charge, right? So not much to figure out there. Sulfate is one of those polyatomic ions, which again is SO4 2-. Once again, this guy is a -2. This guy is a +2. How many of each do I need to balance it out to 0? 1 of each of those will do it, right? So +2 and -2 will get you to 0. So frankly, you just write it straight across. You do not need parentheses in this case because you only have 1 of each. So you don't have to put parentheses or anything like that around any of those. Calcium hydrogen carbonate. I see calcium, which is a metal, and it is group number 2 on the periodic table. That means it has what type of charge? It does have a +2 charge. It's one of those fixed ones. Again, a reminder, as we talked about, right? +1 in group 1, right? +2 in group 2. +3 with aluminum. We skip 4. Going backwards on the nonmetals, group 5 is -3. Group 6 is -2, and group 7 is -1. So again, +1, 2, 3, skip backwards. -3, 2, 1. Yeah, going that way. So hydrogen carbonate, which is also known as bicarbonate, is that one we saw a second ago. That is HCO3 minus. In this case, I am putting together something with a +2 charge and a -1 charge. Which one do I need more of? Yeah, I need more of the bicarbonate. I need a grand total of actually 2, right? That's going to give me a -1 and a -2 to balance out my +2. So when I go to write this formula, I'll go underneath here actually. That's going to be Ca. Do I need parentheses in this case? I do, because I have more than one. So HCO3, and the 2 goes on the bottom there. Yeah. Question on that one there. Lastly, I have ammonium, which is, we talked about at the very beginning, is the one of the few positive polyatomic ions. That was the one we saw in the opening slide there, I think, which was NH4 plus. So that is a polyatomic ion. Once again, having a +1 charge. Sulfide is what? Sulfide is sulfur. Yes. It is not sulfate. It is not sulfite. It is IDE. And again, a majority IDEs just straight from the periodic table, except for those few that are like hydroxide, cyanide, and those guys. So that is sulfur, which is actually group number 6 on the periodic table. So again, 3 skip backwards, 3, 2, 1. So group 6 is -2. In this case, I need more of which one to get me to 0? I do need one more of my ammonium to give me a +1, +2 to balance it out. Again, that is 2 of the polyatomic ion, which means I do need parentheses, right? And a 2, and I just need 1s, right? You could actually count it if you drew it out like this, 1 and 2, and one of those, yeah? So if it helps you to draw it out, do it that way, and you can just count it at the end and put it together correctly. Question on any of those formulas in that case. Okay. There's our chart. All right, so as we talked about there are some of these patterns for those polyatomic ions, and that's really a good way to get familiar with them and sort of group them together by that. And like I said, you could just remember like an 8s and just know how to adjust it up or down, or the 8s and adjust it up or down, whichever way you need to go. By the way, this guy here, for example, ClO3 minus, which is chlor8. Cl is chlorine, which is a group 7, right? You could actually swap out anybody in group 7 in there. So what would you imagine if I put bromine in there instead of chlorine? Instead of chlorate, it is called bromate. Yeah, so it works the same way. That would be bromate. By the way, if I put iodine, which is also group 7, that would be iodate. Yeah, so you could actually swap out anybody there in group 7 in this sort of pattern, and it will basically be named the same way. Yeah. All right. And then obviously our hydrogen in front of it as well. That is one that sometimes tricks up people because, again, the charge does change when you put the hydrogen, because it's really not just hydrogen by itself. It is hydrogen with a +1 charge. So you have to just kind of watch the charge on that, because it does change when you put it there. And again, it's just adding it. Basically, -2 and +1 leaves you a -1 left over. All right, any questions on that? All right, take a little break there, come back, and then we'll do some. Okay, we're going to continue on here, and we're going to kind of transition now into chemical bonding. And we're still going to be really talking about the 2 similar types of compounds that we did with naming. So we're going to look at ionic bonding, and we'll also look at covalent bonding and talk about the differences. So let's take a looky here. So one of the ways that we represent sort of bonding, both ionic bonding and covalent bonding is that we use Lewis dot symbols. Nowadays, people just use more of a generic, they call them sometimes electron dot symbols. It's all the same deal. And basically, a Lewis dot symbol or an electron dot symbol is basically the symbol and one dot for each valence electron that is present. So remember that when we look at valence electrons, they are the outermost electrons. They're the ones in the highest energy levels. They are furthest away from the nucleus, and they're not really held as tightly. And those are the electrons that are involved in bonding. Now, the other type of electrons, which are known as core electrons, those are closer to the nucleus. They are held a lot tighter and they are not involved in bonding. So in bonding, we're not worried about the core electrons. It is only the valence electrons. And a reminder that when you go to the periodic table, as we talked about, you can very quickly determine the number of valence electrons as it equals the group number. So number of valence electrons equals the group number on the periodic table. So everybody in group 1 has 1, everybody in group 2 has 2, 3, 4, 5, 6, 7, and 8 at the end. A reminder that the one exception in group 8 is helium, because it only has 2 total electrons, so it can't have any more valence than it has total. So it has 2 valence electrons in there. Good news is, even though we talked about valence electrons in transition metal region, we never do anything with bonding in this class or in most classes with things in the transition metal region. So you don't really have to worry too much about any of those guys in terms of valence electrons, but they also equal the group number as we talked about. Remember though, that if you're going valence electrons for the guys in the middle, you got to kind of go the normal 1 through 18 numbering, right, to give you the proper number of valence electrons for those guys in the middle. So a Lewis dot symbol, again, is basically the symbol, one dot to represent each of the valence electrons. There really is kind of no major rule about how you should do that. Most people will usually kind of go around one at a time and then pair them up, but it doesn't really matter. The only main rule is you can't really go more than 2 per side. Yeah. So if you go 2 per side, there's 4 sides. That gives you a grand total of how many? 8 valence electrons. 8 is a magical number in bonding because who on the periodic table has 8 valence electrons? The noble gases. That is really the purpose of all bonding, both ionic bonding, covalent bonding, is for everybody to achieve the same electron configuration as the noble gases, which, as we just talked about, is pretty much 8 for everybody except helium is 2. And this is why it's really important, because when you look at the periodic table, hydrogen just needs to get to helium. So hydrogen, 2 valence electrons only. And I say that because people with hydrogen like to go crazy with it. They like to just like triple bond it up and, for good measure, pop some dots around it as well. Before you know it, hydrogen's got 400 electrons around it, and it should not have that. So if you don't want a big X, don't do that. Yes. As I'll remind you as we go through this chapter again, that's pretty much what hydrogen should look like always. Yes. No dots. Don't pretty it up or anything like that. Leave it exactly like it looks like that. It should just look basically with one line, which represents 2 electrons. And hydrogen, again, if you're putting dots all around it, it's definitely going to be wrong. Yeah. It is. We're gonna talk about, but in that particular case, that's usually where we'll see hydrogen in a lot of cases sharing electrons, because it is technically a non-metal. So as we talked about with naming, it will do actually covalent bonding and sharing of electrons. Yeah. So here's a bunch of Lewis dot symbols I made one time when I was bored. I should get a hobby. But you can see there, everybody in group 1 has 1, everybody in group 2 has 2. As we go across there, 3, 4, 5, 6, 7, and 8. Again, helium up there in the top right corner has only 2. Once again, you really don't have to worry about transition metals at all in terms of bonding, so don't even worry about it. So as we didn't talk about with naming, there's really 2 types of compounds. Again, ionic compound, and this again is how we want to recognize it. as soon as you see a metal and a non-metal coming together, that is what should like scream in your head, an ionic bond. That is definitely all you need to know. All you need to identify is that's a metal and a non-metal. That's an ionic bond for sure, which again means that there are no sharing of electrons here. We're going to get a complete transfer of electrons. When you have a covalent compound or covalent bonding, you see that when you see two nonmetals. Yeah. And as soon as you see two nonmetals together, what you should know is there's some aspect of sharing happening with electrons. So as we will talk about, we have sharing of electrons here and no sharing of electrons there. And again, much like what we talked about with naming, it is really important to take a look at what you're dealing with so you can understand what type of bonds happening and, are they sharing electrons? Are they going to transfer electrons? So it's always good to take that moment and try to identify what you're dealing with before you're just trying to jump in there and try to figure it out. A lot of this revolves around those periodic trends we talked about. Things with low ionization energy will tend to form cations. A reminder that ionization energy is the energy needed to remove an electron. So if it has a low ionization energy, you could just look at it and the electron's going to pop off. So it's not going to be very hard to do that. Things with high electron affinity. Electron affinity, again, a reminder, is the energy change that occurs when somebody gains electrons. So if you have high electron affinity, it means you're pretty darn good at gaining electrons. Yeah. So if you have a high electron affinity, that means that you're more likely to gain electrons, become negative, and you will be an anion. As we know from our periodic trend talk, that's our nonmetals that typically will do that, right? They typically will become negatively charged. And our metals over here to the left-hand side of the periodic table are the ones that typically will lose their electrons and become positively charged. So that's pretty much what I just said there. So metals basically going to lose electrons, non-metals going to sort of gain electrons. By the way, that's why with an ionic compound, when we have a metal and non-metal come together, we get that transfer of electrons because the metal's like, take my electrons. Non-metal says, I will because I want them. And we get the electron jump from one to the next. And that's how we get ions that are formed. And that's different, as we'll talk about with covalent bonding, where everybody's in the same location, basically in the periodic table, which means everybody there wants to hang on to their electrons. And they also want to gain electrons. So when two of those guys come together, neither one of them is going to give away their electrons, so they're just going to have to agree to share the electrons. So that's why we end up sharing electrons when we get two nonmetals together because of those periodic trends we talked about. That's why we get a transfer of electrons when we have a metal and a nonmetal get together on opposite sides, basically, of the periodic table. So let's take a look at an example like lithium fluoride. So lithium is group number 1, which means it has one valence electron. So if I draw the little dot symbol for that, and the electron configuration, a little 1s2, 2s1 action. And by the way, right there, that is the valence electron that we're looking at in the picture. So that is the valence electron. These two electrons here are the core electrons, not involved in bonding. And fluoride, which is fluorine, is group 7. So it's got 7 valence electrons. If we did a little electron configuration, 1s2, 2s2, 2p5, these are on the highest energy level. 2 and 5 is 7. Those are the valence electrons that we actually see in the picture here. By the way, when we see lithium, that is a metal, right? Fluorine is a non-metal. So right off the bat, I should know what type of bond I'm going to get here is going to be ionic, yeah? We're going to get a transfer of electrons in this case. And what's going to happen is that lithium is going to share its electron, not really share, but give away its electron, I guess is a way to look at it, over there to the fluorine. The result of that is at that point, Lithium just lost an electron. It now has more protons than electrons, and that is where it becomes positively one charge, right? So it laid up as electron. On the other hand, our fluorine, who started with 7 electrons, just gained an electron. We'll make it red, why not? 1 electron there. Because it gained an electron, now it has more electrons than protons and becomes negatively 1 charge in that case. And now what we have are 2 ions, which is the basis of an ionic compound and an ionic bond. What holds this together is the attraction, which is sometimes referred to as the electrostatic attraction. That's a fancy way of saying positive and negative attracted to each other, opposites attract. That attraction between that, there is absolutely positively no sharing of electrons here. That is also why when we draw it for an ionic compound, there are charges on the right-hand side. Those charges indicate that the electrons are not being shared in this case. And a lot of times people will put a bracket around one like I did, and sometimes they'll put it around both just to indicate, again, that those electrons are not being shared in this particular case. So that is an ionic bond, transfer of electrons from the metal to the nonmetal. The metal then becomes positively charged in a cation. The nonmetal picks up the electron, becomes negatively charged and an anion, and now opposites are going to attract each other and they're going to stick together pretty strongly. That's a super strong attractive force, positive and negative attraction between them. First off, any question on that there? Why does this happen like it does? Well, let's see what happens actually with like the electron configuration. My lithium gave away that electron right there, right? And now ended up with 2 electrons, are an electron configuration of 1s2 when it has a positive charge. Who on the periodic table is number 2? That is helium. Helium is what type of element? Noble gas. That's pretty stable. That's looking good for lithium at this point, right? The fluorine had room right there in the p subshell because the p subshell could hold how many electrons? And it only has 5 at this point, right? So it's going to slap that extra electron right in there and have 1s2, 2s2, 2p6. If I count up the top numbers, that's 2, 2 is 4, and 6 is 10. Who on the periodic table is number 10? Neon. That is also what type of element? Noble gas, yeah? So this, again, is the purpose of all bonding, is for everybody to achieve the same electron configuration as a noble gas, because noble gases are extremely stable. Once again, does lithium become helium in this case? It does not, because protons did not change, right? The only way it could do that is to change protons. And fluorine does not become neon because it didn't change protons. But what it did is it ends up with the same electron configuration as the noble gases, and that creates a super stable bond. And that is really what happens in all ionic bonding, is typically speaking, the metals will lose electrons and back up on the periodic table to the noble gas that comes before it, right? So lithium's over there at 3, and helium's number 2. That is the noble gas that comes right before it. Nonmetals will accept those electrons and move forward on the periodic table to the noble gas that comes after it, creating a really stable sort of bond. Question on that there. By the way, things with the same electron configuration as we talked about are what are known as being isoelectronic with each other, right? Isoelectronic means that helium and lithium with a +1 charge have the same electron configuration. Yeah. Question on that there. So again, like I said, absolutely no electrons being shared here. We have a complete transfer of electrons, which is what creates those ions, allowing each of those elements basically to end up in a noble gas configuration in terms of their electrons, creating basically a pretty stable bond. That, again, as I mentioned, is the whole purpose of bonding. lower the overall energy of everybody to a really stable situation. Let's take a look at another example. Let's say we had calcium and oxide. As we know, calcium is a metal, oxide is a non-metal. So once again, what type of bond here? Ionic, yeah. And again, that is all you need to see to know it's ionic. Trust me when I tell you that. You will not get it wrong if you're asked what type of bond that is. If it's a metal and a non-metal, it's going to be ionic. So calcium is group number 2, which means it does have 2 valence electrons with an electron configuration. I'm just going to shorthand it a little. Argon 4s2. These are the valence electrons that we see in the picture, excuse me. And we have oxide, which is oxygen, as we know from naming. And oxygen is group number 6 on the periodic table. So it's got 6 valence electrons with an electron configuration of 1s2, 2s2, 2p4. Once again, based on those periodic trends, when these two guys get together, calcium's going to go ahead and take my electrons, and oxygen's going to go, cool, I'm going to do that. Thank you very much. Actual conversation that happens there. So this electron is going to come on over here because oxygen can handle it. By the way, if calcium just lays up 1 electron to oxygen, will it be happy? It will not. If you're not sure, you can look at the periodic table. If calcium loses just 1 electron, where's it back up to? Potassium. That's an alkali metal. Doesn't have the same ring as noble gas, right? So calcium here is going to want to get rid of both of those electrons. Good news is oxygen can handle both of those electrons. It's got space right about there because the p subshell could hold 6, and it has only 4 at this point. So we're going to get both of those electrons coming out from calcium. That's going to create calcium now with a +2 charge, becoming an ion. The oxygen there will pick up both of those electrons. And because it picked up 2 electrons, that means it's got 2 extra electrons and a -2 charge to come along with it. Yeah. Again, here, if we look at what happened with the electron configuration, the calcium got rid of its 2 valence electrons, which actually leaves it goes from 20 to 18. And again, that would be our 1s2, 2s2, 2p6, and 3s2, 3p6. Or as you can see there, that is argon's configuration, which is, again, a noble gas, group number 8 there. Also located 2 steps backwards from calcium, right? Moves you 2 electrons, 2 steps back, takes you back to argon. Once again, the oxygen will take both of those electrons right there, giving the oxide a 1s2, 2s2, 2p6, 2, 4, and 10 electrons, which again is neons. Once again here, by losing electrons and gaining electrons, both of these elements have now achieved the ultimate goal of bonding, noble gas configuration, to create this stable bond. Once again here, the attraction that holds this together is that +2 and -2 attractive force, no sharing of electrons here. Actually, that will be held together tighter than the first one. The strength of that charge increases with the size. So +2 and -2 will actually be held tighter than +1 and -1 as well. Question on that there. Yeah. 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 Are you asking what's he writing, like a +2 versus 2+? Is that right? It doesn't really matter. It's okay either way. I personally usually do number first and then the charge. But it's not technically wrong to do it the other way at all. So I think it's just a preference, probably what you just learned when you're younger going through it. But either way is fine. You do need that both combinations there, the charge and the number. So it's fine to do it like I did, +2, or 2+. But if you wrote +2, it's perfectly fine as well. Yeah. But I would say most people will probably roll number first and then the charge, but it's really not wrong at all. Yeah. Other questions? Okay. So what happens though if we scribble all over that page? Let's try it here. What happens if we take our friend calcium that we just did and we put it together with fluorine from the first example? So calcium, again, having our argon 4s2 configuration, our fluorine having 1s2, 2s2, 2p5 in this case. So once again, that is still a metal and a non-metal, so we know it's going to be ionic. We know our calcium is going to give up its electron. So when it does so, it's going to send an electron over to fluorine. At this point, can that fluorine take any more electrons? It can only take one that it just took, right? At that point, it's full. Once again, will calcium be happy just getting rid of one electron? No, it needs to get rid of two. So in this case, it's not just one fluorine involved, but it is a second fluorine involved, which would be more than happy to take the other electron. The result of this is you will end up with a calcium that still has a +2 charge because it gave away one electron to each of the fluorines. You will have one fluorine that picked up just one electron. I'll just circle it. You don't need to circle it, but I will for this purpose. And becomes a -1 charge. Does not become a -2 charge, becomes a -1 charge. The second fluorine, I'll draw it here, also picks up one more electron. Again, I'll circle it there to become a -1 charge as well. Now we have -1, which is -2 and +2, right? The calcium has able to get rid of its two valence electrons, one to each, which means over here, our calcium ion becomes argon's configuration. Each of these fluorines will take one electron in that p subshell. And that means this guy up on top will have a 1s2, 2s2, 2p6, Ra neon configuration. This guy down here will have a 1s2, 2s2, 2p6, Ra neon configuration. Dare I say, all three of these guys now have achieved noble gas configuration. Yeah, they're all perfectly fine. Not a sharing of electrons happening here. Everybody is the charge, basically keeping those guys together. In reality, most people would probably draw it on that side because the minus charges wouldn't want to really be too close to each other, but it's okay. Why is this important? It's important for what we were talking about with naming and all that stuff. When I'm doing naming and writing formulas and I have a calcium with a +2 charge and a fluoride with a -1 charge, how many fluorides do I need to get me to that magical number of 0, right? When I add up the charge, the real reason you do that is this reason right here. It allows everybody to get to that noble gas configuration and actually create a stable bond. That is the reason why when we take ions, we want to put it together in the simplest way that will give the overall charge to 0, because in doing so, that will allow everybody involved to hit that noble gas configuration and be really, really stable. So that's really the reason why we say balance it out to 0. It's actually the bonding reason here is really why we do that. That again allows everybody to get 0. Because as we just saw, if you didn't balance it out to 0 and you just did something like this, you would have a +1 overall charge. And as we saw over here, he would not be happy, right? Because he only gave away one electron, right? So he's not going to be really stable. So again, that is the real reason why when we do ionic compounds, we want to make sure that those charges end up at 0 in the simplest way possible. It's really the bonding reason, getting everybody to that really stable configuration. Question on ionic bonding. Yes, sir. Stability, they are in a sense, but not related to per se what we're talking about here. When we talk about stable and stability here, we're really talking about balancing everything, and that's going to allow really that bond to stay together. Yeah. Reactivity as well, it is related to that. So if you have something that's really unstable, it's going to be really reactive, right? And if you have something that's really stable, it could be less reactive, but it could still be pretty reactive if you put the right thing in front of it, basically, or with it. So um, again, what we're talking about here is there's energy involved in all bonding, right? And everybody has energy, right? Things are moving around. They have a lot of energy. So when we make bonds, the idea is to kind of get everybody together and lower the overall energy of everybody to a more stable situation. And by getting everybody into these really stable electron configurations, that it allows that to sort of happen. Yeah. Other questions? Yeah. Now that we talked about ionic bonding, let's talk about the other type of bonding that we've been talking about with naming. And clearly this one is not fixed. So yeah, those lines miss really badly. I'm just going to redraw those. All right, so covalent bonding is type 3 compounds, basically. That's our two nonmetals together. So again, recognizing what you're dealing with should help you understand the type of bonding that's happening. Should also help you understand what we're talking about with naming, what type of naming or how you should go about naming it. So again, I can't emphasize enough that one of the first things you should always do is try to identify what you're dealing with. Are they two nonmetals? Are they a metal and a nonmetal? So again, it should point you in the right direction. Covalent bonding is sharing of electrons because, again, as I mentioned earlier, this is between two nonmetals, which basically they both want to hang on to their electrons and they both want to take somebody else's electrons. So, like I said earlier, the best that they could kind of agree upon is, hey, let's just share them maybe and try to get everybody happy in that situation. So there is going to be sharing of electrons here. And as we will talk about, that sharing of electrons may be equal sharing or unequal sharing. But there is some aspect of sharing of electrons here, and that is very different than ionic bonding where there is no sharing of electrons. We're just going to see those electrons transfer from one side to the next. So Gilbert Lewis suggested the role of covalent bonding, and hence why we call it Lewis structures, Lewis dot symbols after this guy. So I'm just going to redraw this because I'm not sure what happened to all the dots and stuff. So we had two hydrogens. Obviously, in this case, they are both hydrogen. They're both nonmetals. They're both the identical element, which means they have the exact same periodic trends, which means neither one of them is going to want to give away their electrons. So what they're going to agree upon is let's just share those two guys in this case. And what will happen is they will actually share the electrons between them. So the two electrons between them will count for the hydrogen on the left, and the two electrons there will count for the hydrogen on the right as well. That will ultimately give each hydrogen two electrons. Is that good or bad for hydrogen based on its location on the periodic table? It is good because it's going to move hydrogen now forward to helium, right? And that is a noble gas. So boom, we have just hit some stability there. You can represent this with dots like I showed there, without the circles usually. You can also represent this type of bonding, which is a covalent bond, with a line. And a line would indicate electrons are being shared in a bond. Each line represents two electrons or a pair of electrons. So this is a single bond, which is basically the sharing of two electrons or one pair of electrons. You could have, as we'll see a little bit later, two lines, which is the sharing of four total electrons or two pairs of electrons, and that is a double bond. Or you could have the three pack of lines there, which is a triple bond, the sharing of six electrons or three pairs for a triple bond. And again, most of the time, I would say people will show bonding by using the line, but it is absolutely not incorrect to use dots. So if you want to use dots, you could use dots to represent it. It's not incorrect or anything like that. What holds those together, which is a covalent bond here, is the attraction of those negatively charged electrons So like the nucleus, which is positively charged on each of these, right? So there's a positive charge on each of these guys. Those negative charged electrons between them are attracted to like the hydrogen on the left, but also attracted to the hydrogen on the right. And it kind of locks them in place between the two atoms. And that's what creates the sharing of electrons in this particular case. Any questions on that? And again, in this case, we definitely have sharing electrons. And like I said, that sort of mutual attraction to each nucleus will basically lock everybody into place. Now, if we take something like fluorine, for example, and fluorine again is group 7 on the periodic table, and it will have 7 valence electrons, and we put it together with another fluorine, which also would have 7 valence electrons. Once again, these two guys for sure are going to decide to share those electrons because, again, it is two nonmetals together. So once we see two fluorines, which are two nonmetals, I know I got sharing of electrons happening here. Again, like I know when I have a metal and a nonmetal, I have transfer of electrons. So in this case, we could draw this. A little bit of action there and a little bit over here. And when we share those electrons in the middle, the fluorine on the left will now gain 8 electrons. And sharing those electrons in the middle with the fluorine on the right will also give that fluorine 8 electrons. Once again, on the periodic table, 8 electrons is noble gas, yeah? So noble 8 valence electrons is the noble gas configuration. Again, here by sharing those electrons, they're able to achieve noble gas configuration. Again, we could also represent this with a line to show the bond, which is probably most common the way people would draw it. And again, that line in the middle would represent 2 electrons that are being shared in this case. Question on that there. So when we look at something like this in a Lewis structure and we see the dots and we see the lines, they do represent different types of electrons that are there in this sort of structure. And let's talk about what each of those sort of things represent. And they represent, for example, all those dots which are not involved in bonding. And I know they're not involved in bonding because there is no element on the other side of it. They are what are referred to mostly nowadays as non-bonding electrons, but if you're old like me, lone pairs is what most people call it sometimes. So if you hear somebody say lone pairs or you hear somebody say non-bonding electrons, it's the same thing. They're the electrons that are represented by dots in the Lewis structures. They're not involved in any type of bonding happening. And again, I would say books nowadays kind of use more non-bonding electrons than lone pairs, but sometimes lone pairs pops in there. It probably will pop in from my mouth, to be honest with you. So again, if I say lone pairs, non-bonding electrons, same deal. Now, the electrons there that are involved in a bond has a special name as well, and it's very creative. They are known as bonding electrons, which kind of makes sense. So the actual electrons that are involved in a bond formation are known as bonding electrons. The ones that are not involved in any type of bonding, represented as dots on the Lewis structure there, are non-bonding electrons, are lone pairs. Any questions on that there? When you draw these things, you should always show all those electrons. So you should always show all the non-bonding electrons. You should also always show all the bonding electrons as well. So a Lewis structure, again, is a representation of covalent bonding where we show those electrons being shared through a line or dots. It is important to remember that although we only show the valence electrons in these structures, they obviously have more electrons. They're just not involved in bonding. So, when we show something like, say, lithium or fluorine, fluorine has the 7 valence electrons, but it still has those lower energy electrons as well. They're just not involved in bonding as well. Now, if we take a look at another example of this, water. And water here, by sharing electrons, as you can see in that picture there, I'll draw it up a little bit higher, with the actual two hydrogens, will allow the hydrogen here to end up with two valence electrons. This hydrogen, on the left will also end up with two valence electrons as it shares with the oxygen. And the oxygen, by actually sharing with both of those hydrogens, will hit that magic number there of 8. And again, through all this sharing of electrons, everybody again is able to hit that noble gas configuration, which, as I mentioned a number of times by now, is really the whole purpose of all bonding, basically, is for everybody to end up basically right over there in group number 8 in terms of their electron configuration and be really, really stable. So that brings us to what we've kind of been going around. The official name, obviously, for 8 in bonding is what is known as the octet rule. And the octet rule means 8, basically. It means that everybody will continue to make bonds until they have 8 valence electrons around them. So they'll just keep on going until they get 8. Except for who that should never have 8? Not helium, but the one before it? Hydrogen, yeah. So again, hydrogen never have 8, should only have 2. And that is sometimes what is referred to as the duet rule. And like I said before, never hurts to say it because I've seen a lot of weird looking hydrogens come through pages. It should pretty much always look like this. It also means that when you are drawing pictures, you should keep in mind that hydrogen should never be in the middle of the picture, because if it's in the middle of the picture, it most likely will have way more than 2 electrons. So hydrogen should always be on the outside, just hanging on by 2 there, and never in the middle because it will also have way too many electrons. Okay. So multiple bonds, as we kind of talked about on the previous slide, there are single bonds. Now, the idea here is this: sometimes to get people to the octet rule, all you simply need are single bonds. Single bonds are perfectly good to do that. Gets everybody to the octet rule. Once again, the single bond, as I said earlier, a single line to represent it that represents 2 electrons or a pair of electrons. A double bond is actually sometimes needed to get people to the octet rule. So sometimes single bonds are not enough to get everybody to that stable configuration. You need a couple extra bonds there, and you're going to need to make some double bonds. CO2 is an example of that. So again, CO2 actually will make a double bond on both sides, and that is actually necessary for everybody to get to 8. So how does everybody get to 8 in this case? Well, if we just kind of highlight things, this oxygen has 2, 4, 6, and 8 through the double bond there. This oxygen on the right, 2, 4, 6, and 8 electrons. The carbon in the middle will also have 8. I'll use a different color maybe. 2, 4, 6, and 8 electrons. So in this case, in order for carbon to actually be happy and get itself to 8 electrons, it actually needs to lay up a couple double bonds. And that's sometimes the case. Sometimes it may just need 1 double bond will be sufficient, but sometimes you may need 2 to get yourself there to that. Again, a double bond is 2 lines representing 4 total electrons, are 2 pairs of electrons. And sometimes double bonds is not enough to get everybody back over to the noble gas configuration. So sometimes you do need triple bonds to do that. And a triple bond is, as we can see here in nitrogen, nitrogen actually needs to make a triple bond with itself to be happy. This guy will see in organic chemistry. Those carbons there actually needs to make a triple bond as well with itself to be able to do so. That's going to give hydrogen 2. This carbon here, 8. This carbon here, 8. And that hydrogen there, 2. So that's going to give everybody the stability that they need. 1, 2, 3 for a triple bond. 6 pairs of electrons. Oh, not the pairs. 6 total electrons 3 pairs of electrons. Side note on this, when we talk about drawing these things, sometimes people get carried away with it and they just want to like double bond out of the box, triple bond out of the box because that looks more chemistry like, right? So I'll just tell you this now and I'll tell you it again. You shouldn't do that. Yeah. So you should really start with single bonds. And if that doesn't work, you should then go to double bonds. And if that doesn't work, you should go to triple bonds. In most cases, double bonding or triple bonding right out of the box, not going to get you the right picture. Yeah. So you kind of want to go in that progression, single bond. If that doesn't get everybody there, double bond. If that doesn't get it, triple bond. That should get it. Or you did something wrong at that point. In most cases, you probably won't go more than that. So let's talk about this sort of sharing of electron and how we know how the sharing is going to happen. So we're talking about covalent bonding and we're talking about sharing of electrons. And as I mentioned before, that sharing can be equal or it may be unequal sharing of those electrons. And it is that electronegativity, which is really the big factor to determine how electrons are going to be shared. You could also use electronegativity to help you determine if you have an ionic bond, but the truthful answer is you don't need it because I know I have an ionic bond when what two things come together? Yeah, so as soon as you see metal, non-metal, that's all you need. You don't need anything other than that. But for covalent bonding, when we do have sharing of electrons, electronegativity can be very helpful for you. Again, a reminder is, I think we talked about it when we did some periodic trends. Electronegativity is the ability of an atom to bring electrons towards itself. And on the periodic table, also known as a square, it increases as you go up to the right and it decreases as you go down to the left. Fluorine is the most electronegative element you could have. And that is because if you look at the periodic table, fluorine is as far up and to the right as you could go. Everybody to the right of fluorine is a noble gas, which means they're perfectly fine by themselves. They're not looking to do anything and they're not looking to react because they're already stable and stuff like that. So how can we use electronegativity and what helps us decide, how electrons are shared? If we take an example like H2, obviously in this case, they're going to be sharing those electrons. And in the case of hydrogen on the left and the hydrogen on the right, they are the same hydrogen basically, right? They have the exact same electronegativity, which means when these electrons in this case are shared, they are actually going to be shared equally because they're both going to pull those electrons exactly the same. Kind of like tug of war, right? If somebody pulls the rope on each end equally, the little flag in the middle is not going to go anywhere, right? It's just going to be stuck there. So if you take a look at this and this kind of red smear or whatever I'm drawing up here is the electron density, we're going to have kind of equal sharing of electrons. And when we have equal sharing of electrons, that is what is known as a nonpolar covalent bond. I would say most people leave the covalent out of it and just call it a nonpolar bond. So they are the same, basically. It is usually implied that if it's a nonpolar bond, it's covalent, they're sharing of electrons, and they're equal. Because these electrons are going to be shared equally, this is essentially a neutral bond. There is no like positive side, there is no negative side. All the electron negative stuff is all spread out nice and equally. Everything's sort of balanced. So this is kind of like a neutral or no charge situation happening in this bond. Again, there is no positive side or negative side. And that is a nonpolar covalent bond, equal sharing of electrons. Now, what would happen if I swap out the hydrogen or one of them for fluorine, for example? Now, in this particular case, based on electronegativity values, which one is more electronegative? Is the fluorine, is the most electronegative. So what's going to happen in this case is the electrons are going to be more attracted to the fluorine side than the hydrogen side. So what's going to happen is, if I kind of do my little bad scribble here, if this is like electrons, most of them are going to hang out over there on the fluorine side rather than the hydrogen side. What that does is it makes the fluorine side, if you had to guess, more positive or more negative. If all the electrons are hanging out on fluorine, it should be more negative, right? Electrons are negative. So it creates a partially negative charge on the fluorine. That's a delta symbol. It means partial negative. It also creates a partially positive charge on the hydrogen because the electrons are moving away from the hydrogen. It's becoming what is referred to as being electron deficient, right? It's losing like those hydrogens. You can represent this as well with an arrow. And this arrow is what is referred to as a dipole arrow, where it always points to the more negative side of the bond. And the back part that kind of makes like a plus sign is the more positive side of the bond. And this is what is sometimes referred to as a dipole arrow. These electrons are now not being shared equally. So no equal sharing, right? Or unequal sharing, I guess is another way to write that. This is what is known as a polar covalent bond, or just a polar bond. Final question of the evening. Why are these partially negative charges and partially positive charges? And why are they not full positive charges and full negative charges? Yeah, so it has to do with when we're talking about covalent bonding, what is happening with those electrons? Are they being transferred or shared? Being shared, yeah. So even though they're not being shared equally, there is still some aspect of sharing. If you want to go back to the tug of war example, the hydrogen is just barely hanging on to that rope. The fluorine is dragging it across the grass, right? But he's still hanging on. So because there's still some aspect of sharing here, we get actually partially positive charge and partially negative charge. In an ionic bond where there is no sharing of electrons, we get a full transfer of electrons from the metal to the non-metal, and that's what creates the full positive charge and full negative charge. All right, we were